I'll talk about an algorithm for hazard pointer protection of structures with immutable links. First, for background, I'll give a brief example of how hazard pointers work for safe reclamation. So here we have two threads. One is trying to access an object, and another thread wants to remove it concurrently and reclaim it. So the first thread will read a reference to the object from a shared source. It sets a hazard pointer to it to protect it, and then checks that it hasn't been removed already, so it will be safe to access it. And then we have the other thread remove the object, but it cannot reclaim it yet because it's protected by a hazard pointer. So the first thread will go and access the object safely, and then when it is done with it, it clears the hazard pointer. So then it will be okay for the removing thread or a different thread to check that it's unprotected and then reclaim it. So we get safe reclamation this way. There are many advantages for the hazard pointer algorithm in terms of like speed and scalability and progress guarantees and immunity to delays. But then there's limitation for its protection of linked structures. So looking at this example of a single linked list where we have a thread that is protecting an object A with a hazard pointer, but then we know that it's not protecting the rest of the objects. If it wants to traverse to node B, that's not guaranteed. So you can have another thread that removes nodes A and B, and A is protected, but B is not. So actually, B could have been reclaimed already. So and the thread cannot just traverse to node B. Existing algorithms we can do hand-over-hand traversal using two hazard pointers. That works, but then it's conditional. So there's no guarantee that if our thread wants to access node B, that it will get to it. It might start over from a safe point like the head of the list. So that doesn't always work for all uses. Another alternative is to add a layer of link counting on top of hazard pointers, but then that would give us unconditional traversal, but it has the problem that we cannot retire a node until we reclaim its ancestors. So that we would get in a situation which is it's not uncommon to have a process with like tens of thousands of hazard pointers and a long list that's, let's say, 1,000 nodes. We would have to check all the 20,000 hazard pointers to reclaim each of the nodes. So that can be impractical for important use cases. So now we get to the algorithm. You can look at the pseudocode in the paper, but here's the outline of the algorithm is that we're applying link counting, but we're integrating it into hazard pointer algorithm. So we're adding to that, we consider all potential protection by hazard pointers to be equivalent to one implicit collective reference. And then we're applying this to immutable links. So actually we can consider these links, these counts to be commutatively released. So you can release the protection by hazard pointer first, or mixed with the release of the link counts coming from ancestors. So the general rules are: if you find the node unprotected by hazard pointers, then you release its implicit reference. If you reclaim a node, then you release the links to its children. And when a node has all its links and reference released, then you can reclaim it. So let's look at a specific example here where we have a long structure that we can, and actually show that we can reclaim it in one pass. So here you have none of the nodes are protected. We get nodes A, B, C, D removed and retired to the hazard pointer library. And now at some point, some thread will decide to try to do reclamation. So it will read all the hazard pointer values. So there could be tens of thousands of these, and that's our one pass. Then it will go to check each of the retired nodes against these values that it read. And that can be in any order. So we're going to just random order here. C, D, A, B. So we check C, it's not protected. We get the count down from 2 to 1. Okay, and now we check D, again 2 to 1. We check A and goes from 1 to 0. So now, because it's a count 0, so we actually reclaim A and release the link to B. Now we check B against hazard pointer values. It's unprotected. The count goes from 1 to 0. Now we can reclaim B and release the link to C. Again, D, we reclaim C and release the link to D. And finally, reclaim D and release the link to E. So we were able to reclaim any number of nodes with their ancestors in the same path. So the features of the algorithm is that it allows unconditional traversal for structures with acyclic immutable links. It allows the reclamation of nodes in the same path as their ancestors. Let's say if none of them are protected. It adds zero computing cost to protection operations, which are the common ones, are the critical operations that we need to careful about their performance. This is at the cost of adding a counter to each node that is capable of holding the number of inbound links. And we may be adding 1 or 2 atomic operations per inbound link for per lifetime of each node. So this is implemented as part of the Facebook C++ open source library. You can find it on GitHub. It's part of the hazard pointer implementation. We have the original implementation, also this one with this algorithm that extended to link structures. You can see on the left, there's the results for protection and traversal operations. These are critical, frequent operations. And you can see it's extremely low cost. For example, protecting one object can be as low as 2 nanoseconds. Traversal, so with hand over hand, of course, we're doing more. We're changing hazard pointers frequently, whereas with the new algorithm, we just need to protect the head of the list and traverse the rest of the list, the same as sequential traversal. And it's basically perfectly scalable. We get the same kind of numbers with any number of threads, concurrent threads. Reclamation has an extra cost because we're doing extra atomic operations for releasing the inbound links. But then note that reclamation is done asynchronously, and it's an amortized operation that's done infrequently. In summary, so I described an algorithm for unconditional traversal of structures with immutable links. No cost to the critical operations of protecting objects at the cost of adding a counter and managing the counter. You can check out the implementation in the Folly open source library. And thank you for watching.